Hello everyone and welcome back. Today we're going to continue our exploration of linear algebra and focus on an extension into the realm of 3D geometry. Before we get into that, we need to introduce a concept known as the cross product between two vectors, and we're going to be calling these vectors u and v. So let us assume that u and v are both vectors in the vector space R3, and let ik be the standard unit vectors of R3. In particular, I1 is going to be 1, 0, 0, I2 is going to be 0, 1, 0, and I3 is going to be 0, 0, 1. So IK is just going to be equal to a bunch of zeros except for 1 in the kth position, or the kth row of that vector. So we define the cross product between u and v, and we're going to be denoting it by u cross v, and the result is going to be a vector, and that's very important to keep in mind. Because remember, when we did the dot product between two vectors, the dot product of two vectors is going to give us a number, but the cross product between two vectors is going to give us another vector. And you can find that vector via this cross product operation via the determinant of this 3 by 3 matrix, where we have the standard unit vectors in the first row, u on the second row, and v on the third row. I guess you could think of them as the transpose of u and the transpose of v more formally. Alright, so that's the definition of a cross product. So let's just do a quick example on how to calculate a cross product, and then we'll get into the interpretation of why we actually need it. So let's start off by defining two numerical vectors in R3. So let's start off with defining u to be equal to 1 minus 3, 2, and let's define v to be equal to minus 3, 4, 1. So the cross product of u and v is going to be equal to the determinant of this matrix I1, I2, I3, 1, minus 3, 2, and minus 3, 4, 1. In case you don't like writing the column vectors as rows, keep in mind the determinant of a matrix is equal to the determinant of its transpose, so you technically could do the determinant of I1, I2, I3 in the first column, u in the second column, and v in the third column, and you'll get the same exact answer. So let's do our usual operation for the determinant of 3 by 3 matrices. So this is going to be equal to I1 times the determinant of minus 3, 2, 4, 1, minus I2 times the determinant of 1, 2, minus 3, 1, plus I3 times the determinant of 1, minus 3, minus 3, 4. So that's going to give us I1 times minus 3 times 1 is minus 3, minus 8, and then minus I2 times 1 plus 6, plus I3 times 4 minus 9. So minus 3 minus 8, that's going to give us minus 13. So minus 13 I1. And then we're going to have 1 plus 6 is 7, so we're going to have minus 7 I2. And then 4 minus 9 is going to be minus 5, so it's going to give us minus 5i3. That's right, so that is our result. Now we can switch this back into matrix form, because keep in mind this is going to be the same as negative 13 times 1, 0, 0, minus 7 times 0, 1, 0, and then minus 5 times 0, 0, 1. Therefore, we can see that the cross product between our vectors u and v is just going to be equal to the vector minus 13, minus 7, minus 5. So indeed, the cross product between two vectors does give us another vector also embedded inside of R3. So that's how you can calculate the cross product between two vectors. Here are two theorems associated with cross products that you definitely should be aware of. The first one is very simple. The cross product between two vectors is not commutative. In particular, u cross v is not equal to v cross u, it's equal to the opposite of the other one. So, what is the relationship between a vector and the negative of that vector? The difference, of course, is not the magnitude. It's going to have the same exact magnitude, but it's going to be in the opposite direction, right? So if you connect u with its opposite, negative u, that pretty much will create a line in this sense, R3. I'm not going to prove this here. I'll leave that for you. It should be very straightforward, though. Now, the second theorem is very, very important, and that's going to lead us into our next example. So let us assume we have two vectors u and v that are both belonging to R3. And let's define n to be equal to the cross product between u and v. Then n, that cross product between u and v, is orthogonal to both u and also v. So what does that mean? So that means n dot product with u is equal to 0, and n dot product with v is also equal to 0, even if n and u are both not equal to the 0 vector, because that would be a trivial situation. In particular, if you have n or u dot product with the cross product n, which is just going to be u cross v, that's going to be equal to 0. And we can also say that v dot product with u and v is also going to be equal to 0. Of course, we can switch that because, if you include a negative sign, that's not really going to change anything. We can also say that u dot product with v cross u is equal to 0. And also v dot product with v cross u, that's also going to be equal to 0 as well. Now that theorem is an algebraic proof if you want to sort of go ahead and do that, but also not very difficult in case you want the challenge if you're in the theoretical interest. Now let's look at this from a geometric perspective and sort of see what's going on here. So let's assume that we have a vector u that's going in this direction, and let's assume we have another vector v that's going in this direction. So the cross product between these vectors, and keep in mind this angle doesn't have to be a right angle, it could be literally any angle. The cross product is always going to be a vector in this direction. So n, this is the cross product of u and v, and the angle between that red and those black lines is always going to be a right angle. Now, you cannot just draw this red arrow in any particular direction. For example, in this case, you cannot draw it going downwards. That would be minus u times v, or in particular, v cross u. So in order to make sure you have your direction straight, this is usually what we refer to as the right hand rule. So how does the right hand rule work? So if you use your pointer finger on your right hand to be associated to the vector u, so this is going to be your pointer finger on your right hand, and let's assume that this is your middle finger, V, also on your right hand, and you sort of curve them in that particular direction, then your thumb is going to be this particular vector facing upwards or downwards depending on the orientation of U and V. So if we look at a different orientation of these vectors, for example, let us assume we have u in that direction, we have v in that direction, and let's assume we have some angle there, u cross v is going to be this vector here, right? And why is that? So keep in mind that is going to be your pointer finger, this is going to be your middle finger, and this is going to be your thumb. So this is going to be u cross v. So in this particular case, generally your hand would be upside down in order to make this picture, right? So your pointer finger would be facing forward, your middle finger would be facing to the right, and your thumb would be facing downwards in this particular case. If you want a vector in the opposite direction, in particular this vector, that's going to be v cross u, which as we already know is going to be the opposite direction of u cross v. Right? So that is what we call the right-hand rule in order to determine which direction your normal vector is what a lot of people call it, and also the direction that normal vector is going to have with respect to the two vectors that you were taking the cross product between. Now that we've defined the cross product between two vectors u and v in R3, now we're actually going to use it to derive the equation of a 3D plane in R3. Keep in mind, a 3D plane in R3 is just a two-dimensional linear subspace of R3. So it's just going to be, just a plane, a little flat plane, almost like a table or something that's sort of slanted or flat or vertical or horizontal or something like that, and it's just sort of hanging out in three-dimensional space. So if we've characterized that 3D space in terms of the coordinates x, y, and z, then there should be some equation of that plane that's going to be written in the form ax plus by plus cz is equal to, say, d or something along those lines. And one, of course, can show that if d is equal to 0, that means the origin is, of course, a point in that particular plane. Right? So this is some basic 3D geometry that you should be aware of. So let's assume we choose 3 particular points in that plane, and we're going to be calling them P0, P1, and P2. And let's assume that their coordinates have that particular structure. Let's see if we can create two vectors u and v that goes in the direction of p1 from p0 and also from p0 to p2. So what we're going to be referring to in terms of p0, this is going to be what we refer to as a reference point. This is just to help keep things sort of organized from our end. As long as you stay uniform, you could use P1 as a reference point or P2 as a reference point. As long as you stay consistent, that's all that matters. So let's see if we remember how to do that. So recall that a vector u that has a base point P0 and is in the direction of P1, and also P2 is going to have a similar structure, is given by u is equal to P1, the vectorized version, minus P0, the vectorized version, which from our definition of our points, is just going to be equal to x1 minus x0, y1 minus y0, and z1 minus z0. And v is going to be in the direction of p2 from p0. So that means this vector here is going to be equal to u, and this vector here is going to be equal to v. That's going to be equal to p hat 2 minus p hat 0. So p0 still is the reference point. That's going to be x2 minus x0, y2 minus y0, and z2 minus z0. Okay, so those are the vectorized versions that sort of characterize the plane that we're working with. So if P0, P1, and P2 do belong to this plane, that means the vectors u and v also lie within this plane as well. In particular, one should be able to show that if P0, P1, and P2 do not all lie on the same exact line, these vectors u and v will be independent vectors, and the span of u and v actually is this plane P, which is actually very, very important to understand. Now let us take a broader look at the picture we're actually working with. What I've done here is I've embedded our little plane P, which is shown here in these green lines, or that's pretty much like the mesh grid of our surface. And I've embedded it in 3D space, and I'm showing the X, Y, and Z axis for which I've sort of, organized my 3D space into. So I've named our reference point P0 to be that corner point there, and now what I'm going to do is I'm going to choose any other point inside of this plane. I'm actually going to call it P, so let's make this P a little bit more fancier, because I'm just going to call this point right here, I'm going to call that just P. Now, let's look at these points P0 and P from the vector perspective. So if I want a vector in the direction of P0, that's just going to be this vector here, right? So that's going to be the vector p hat 0. And if I want a vector pointing in the direction of p, that's going to be this vector right here. So that's going to be p hat. Now what I want to do is I want to consider a vector that sort of connects these 2 points. You can choose either direction. Let's assume we choose this particular direction. So from P pointed in the direction of P0. So we know that that vector there is going to be P hat 0 minus P hat. Right? So here we're assuming that P is any point x, y, z that belongs to our plane. Okay, so that is our assumptions here. Okay, so from this picture, you should be able to verify, or you should be able to sketch out a proof that if P0 belongs to our plane, because it's our reference point, that's how u and v were constructed, and P also is an arbitrary point belonging to our plane, and doesn't matter where that point P is. It could be P0, it could be P1, P2, or any other linear combination, assuming that U and V are independent, of course, for which they span that particular plane. Then you should be able to verify that P hat minus P0, and also it's reverse direction, so we could go in the opposite direction as well. P0 minus P hat 1, both lie in our plane P as well. Okay, so now let us bring in our normal vector. So our normal vector is going to be equal to what? So if this is our pointer finger and this v vector is going to be our middle finger, where is going to be our normal vector? So our normal vector is going to be pointing downwards, right? So that is going to be our normal vector n, which is going to be the cross product between u and v. And if you want the upwards vector, that's going to be equal to v cross u. Both of them are going to be normal to our plane, but I'm going to be focusing on the cross product u and v, right? So what's so special about this? So if m is the cross product of u and v, that means n dot product any u is going to be equal to 0, n dot product v is going to be equal to 0, and also n dot product p hat is also going to be equal to 0, where p hat is any vector in our plane P, right? That's the most important one. So regardless of where this point P is, the vector associated with it, for example, P hat 0 minus P or P minus P0, whichever vector you're interested in. I guess I should be writing that instead because I have P hat written there. So let's just write it as n dot product with, let's do P hat minus P hat 0. Right? That is going to be equal to 0 because p hat minus p hat 0 is going to belong to our plane, so n is going to be orthogonal to it. So what exactly does this dot product equation give us? So if we look at this, and in particular that difference vector, that means that nx times ny times nz, let's assume that that is our normal vector m, dot product with p, well p is just an arbitrary vector x, y, z, minus p0, which is going to be x0, y0, z0, that's going to be equal to the 0 vector, 0, 0, and 0. So if we do that dot product out, what are we going to get? So we're going to get the equation of our plane P, which is going to be equal to nx times x minus x0 plus ny times y minus y0 plus nz times z minus z0 is equal to 0. And that is the equation of a plane, right? So that's the equation of a plane, where n is our vector that is orthogonal to that plane, and x0, y0, z0 is just a reference point in that plane. Since the derivation of the equation of a 3D line, at least from our approach, is a little bit tedious, let's look at a numerical example to sort of see how we can construct the equation of a 3D plane that passes through these 3 points, just to see how that would look like in practice. So let's assume our goal is to find the equation of a 3D plane that passes through these points A, B, and C. So the very first thing we need to do is choose our reference point, and keep in mind it doesn't matter which reference point you choose, but I'm just going to choose A since, I've just named it as the first letter in the alphabet or something like that. So once you choose your reference point A, then we're going to construct our vectors u and v. So u is going to be the vector b minus our reference vector a. V is going to be our vector c minus our vectorized version of a. So that's going to give us what? So that means u is going to be equal to b, which is going to be equal to 2, 1, 0, minus a, which is going to be 3 minus 2, 5, which is going to be minus 1, 3, minus 5. And then v is going to be equal to c, negative 3, 1, 4, minus a, which is going to be 3, minus 2, and 5. So that's going to be minus 6, 3, and minus 1. So those are our vectors u and v. Now I'm going to look for the cross product between u and v, and that's going to give us n, which is the first major component for our equation. So n is going to be the cross product between u and v. And remember, that's going to be equal to the determinant of our standard vectors I1, I2, I3, and then u, negative 1, 3, minus 5, and then v, minus 6, 3, minus 1. So what is that going to come out? So let's just do that right quick. So that's going to be equal to I1 times minus 3 plus 15 and then minus I2, which is going to be equal to 1 minus 30, and then plus I3, which is going to be minus 3 plus 18. So that means our normal vector n is going to be equal to the vector 15 minus 3, that's going to be equal to 12. 1 minus 30 is minus 29, that changes to a positive 29. And then we're going to have 18 minus 3 is going to be equal to 15. So that is our vector that is normal to the plane. And keep in mind, if you use another reference point, you might get a different, well, you probably most likely will get a different normal vector, but it's still going to be normal to the plane that those points are embedded in, which is very, very important. Now keep in mind what was our reference point, A. That was going to be equal to 3 minus 2, 5. So that means that's going to be our x0, our y0, and our z0. That's going to be our nx, that's our ny, and that's going to be our nz. That means we can construct the equation of our plane. So what is that going to look like? So that means our plane is given by, so 12 times x minus 3 plus 29 times y plus 2, and then plus 15 times z minus 5 is equal to 0. So let's distribute and then isolate our constant to the right-hand side. So that's going to give us 12x plus 29y plus 15z is equal to positive 36 minus 58 plus 75. That means our equation of our plane is given by 12x plus 29y plus 15z is equal to 53. And you should be able to verify if you plug all those 3 points in, you will get this, they will satisfy this particular equation. Therefore, this is the equation for which those 3 points lie. The next problem that we're going to look at is the following one. Suppose we're interested in finding the area of a parallelogram that contains these 3 points in 3D. Now you may have seen a problem like this in the two-dimensional world. So remember, if we're in the two-dimensional world, if we have our coordinate system x and y, let's assume we have u and v located here, we can always make a parallelogram by transposing u and transposing v here, and that's going to generate a parallelogram. Now question, how do you find the area enclosed by these vectors? So one can show that that's actually equal to the absolute value of the determinant of u and v. Right? So it's the determinant of that 2 by 2 vector. So is there a nicer, or is there an extension of the area of a parallelogram in 3 dimensions, right? So actually, yes, there is. So the theorem that we're actually going to prove is that the area of our 3 by 3 parallelogram is going to be the norm of the vector u cross v. So if that's the case, well, how do we do it? So if we look back at our example, let's assume that we want to find the area of the parallelogram that's spanned by those particular vectors. We would first have to find the cross product, which is the same exact example as before. So that means the area is going to be the norm of the vector 12, 29, 15. So that means the area is going to be equal to the norm of u cross v, which is going to be equal to the square root of 12 squared plus 29 squared plus 15 squared, we know is 1210, which is going to be approximately equal to 3479. So that is the area of that parallelogram spanned in 3D. Now for this theorem, let's see if we can go ahead and give a nice little proof for that result, and we'll close out with that. So proof. So what is the norm of u cross v? Let's actually look at the norm squared so we don't have to deal with that square root. So we know that a vector's norm squared is actually just the same thing as that vector transpose that vector, or the dot product of that vector with itself. So u cross v, dot product with u cross v. So if we look at these vectors u and v from their component form, u1, u2, u3, and then v, similar, v1, v2, v3, when you multiply, if you do the cross product between u and v, you actually get a nice little symmetry property here. So you should be able to show that u cross v is actually going to be u2, v3 minus u3, v2, u3, v1 minus u1v3, so it's backwards of the typical orientation. u1v2 and then u2v1. So we're going to do the dot product of that with itself. u2v3 minus u3v2, u3v1 minus u1v3, and u1v2 minus u2v1. And we know how to do the dot product. We do, you take that and we multiply by that. So it's the first component squared, plus the second component squared, plus the third component squared, and then we have to FOIL those things out. So after you perform some nice little fun algebra, you're going to get the expression u1 squared plus u2 squared plus u3 squared times v1 squared plus v2 squared plus v3 squared minus u1 v1 plus u2 v2 plus u3 v3, the quantity squared. And keep in mind there is some fun algebra between these steps. So what exactly is those expressions? Well, that's precisely equal to the norm of u squared times the norm of v squared minus, and that's just the dot product of u and v, right? So keep in mind a nice little geometry formula that we derived back when we were talking about the angles between two vectors. We can represent the dot product as the norm of u times the norm of v times the angle of the angle times the cosine of the angle between those vectors u and v. So if we look at that from the geometric perspective, if u is there and v is there, theta is going to be that angle there. Right? So using that little expression and substituting it there, we will get what? So that's going to be equal to the norm of u squared, the norm of v squared, minus the norm of u. Remember, we're squaring that, right? Then we're going to have the norm of v squared, and then we're going to have the cosine squared of theta. We have a common factor here, norm u squared, norm v squared, so we can factor that out. So once we do that, we're going to have norm of u squared, norm of v squared, and keep in mind this is the norm of u cross v squared times 1 minus cosine squared theta. From the Pythagorean identity, we know that that's equal to sine squared. So that means the norm of u cross v is going to be equal to the norm of u times the norm of v times the absolute value of the sine of the angle between those vectors. My claim is that this actually tells us that this is the area of the parallelogram associated by u and v. Now, why is that the case? So let's look at the picture of our parallelogram that we're actually considering here. So let's assume that that's u and that is v. So that's u, that's v. Let's assume that that's drawn to scale. So that means those angles are equal and those angles there are actually equal to each other. And let's assume we have a nice little angle there, theta, and let's drop a vertical line there. So how do you find the area of a parallelogram? So keep in mind that parallelograms are just two-dimensional subspaces of the three-dimensional space that we're actually working with. So we can actually just view this just as a 2D geometry problem, even though it's most likely going to be rotated in our 3D space. So that's going to be equal to b. But b, at least in this picture, is going to be equal to the norm of v. So what's the height going to be? So the height, which I'm just going to call h, so the sine of theta is going to be equal to the opposite over the hypotenuse of that triangle, which is going to be equal to the norm of u. So we see that the height of this triangle, or the height of this parallelogram, is just going to be equal to the norm of u times the sine of h, right? Now one may be thinking, well, where would that negative sign come from? Because notice we have an absolute value there. That would be referencing this particular angle there and its mirror image, right? So that's where the absolute value would be generated from. And keep in mind that the area of a parallelogram is just going to be equal to base times height. So we have the norm of v times the norm of u times the sine of h, and that of course gives us the area of the parallelogram generated by u and v. So those are some geometry applications associated to matrices, vectors, and in particular cross products in order to help us find the area of parallelograms both in 2D and 3D space, and also how to find the equation of a 3D plane. So I hope you enjoyed, and I'll see you in the next video. Take care.